Check it out now, y'all.
NanoHub U, online instruction.
Welcome back. We are talking about selectivity of nanobiosensors. In the last lecture, I discussed one of the ways that incorrect binding between two DNA molecules can give you a false positive. And the main point of that lecture was that if you bind things correctly, then it has a certain amount of energy that you need in order to break it. Incorrectly bound ones have a little bit less energy it requires to detach them. So therefore, if you can increase this difference by designing the DNA correctly, then by using the temperature as a probe, you can wash away all the incorrect bound ones. Let me tell you about a second sensor selectivity problem that is again fundamental, and we have to sort of work with it. Recall that we had this target molecule that we really want to capture, the red molecule. This is a correct conjugation. The first one, red molecule, has been collected or conjugated by the correct sensor, so which is the signal we desire. The red is the signal that we desire. It turns out that if you have a lot of blue parasitic molecules that incorrectly binds to the sensor, then that gives me a false positive. And this is something we discussed in the last lecture. Today, I want to focus on the black term. And the black terms are parasitic molecules which sort of sits on the sensor but doesn't conjugate with the target molecule or receptor molecule at all. But it is sitting there physically close to the sensor surface and therefore will induce a false signal in the sensor, something that we have to avoid. So what we'd like to see that where are these empty spaces where the molecules can land. And again, the goal is to reduce beta. Remember, in beta, I have this number of components, parasitic components. And so we want to reduce this as much as possible. The first term NT prime, we could reduce it by enhancing the temperature and washing it away. Now let's talk about this black term called N geometry, how we can reduce it so that we can reduce beta and the noise term associated with it. Okay. So today I'll focus on the empty spaces. Let's say you have a sensor and this is the top view, and all those little circles you see everywhere, the little ones, those are the receptor molecule and the target molecule. And let's say they have been captured, leaving behind a lot of empty spaces where this is a top view. So where in these empty spaces, a parasitic molecule can just sit on top. And if you have a biosensor underneath, the biosensor may think that it has caught a molecule, like a potentiometric biosensor. It may think that it has caught a molecule. Actually, this is not the right molecule to begin with. So which is a concern. So what we would like to see, how much empty spaces you have. And couldn't you simply eliminate the empty space by packing things densely? It turns out that you cannot. It turns out no matter what you do, you cannot cover more than approximately half of the total surface. Other half remains empty. And that was a big surprise. Let me explain where that thing comes in. And by the way, this is a game you can play with somebody, as I will explain also in a second, and convince yourself. So today I'll be talking about as a selectivity problem arising from random sequential absorption. So the molecules are coming down randomly, one after another, and sequentially getting absorbed on the sensor surface, the physics of it. And then I will derive a corresponding limits, show you some results before I conclude. Think about a periodic array arranged nicely. We all know that if the total amount of fraction of area covered is essentially pi r squared, that's the area of the blue circle, and divided by, if the diameter is 2r, so the box that contains the circle is 4r squared. You divide pi over 4 is 78%. So 78%, if things are nicely arranged, 78% of the area is covered. 22% empty spaces, white spaces, which is bad because here the molecules, other molecules can come in and sit and so therefore give a false signal. Of course, you can immediately say, no, there is a way to do better. How do I do better? Well, if I put it in a sort of an hexagonal lattice, then I know you can calculate that approximately 90% of the area is covered, two-dimensional area. We are looking at the top view of a sensor surface, and these blue are the receptor molecules. And there are only about 10% of the area left. Now, this would be very good. If we could do that, arrange things like this, it will be very good because there will be very little empty spaces where a parasitic molecule could sit and cause trouble. It turns out that if you throw things one at a time, like a child putting a penny on a two-dimensional surface, it turns out that, and if they are sort of get stuck, let's say it's a glue, it gets stuck, and then it will turn out that if you try to bring any more, you cannot put it in because it doesn't fit. And eventually, at steady state, you will only have slightly more than half you can fill. No matter what configuration you try, no matter how you throw it, every time it will be a different configuration because it's a random process. But at the end of the day, when you are done in a large enough circle, you can only cover about half. The remaining half will remain empty and susceptible to parasitic absorption. Now, this would be a big problem. Where is this 54% number come from? Well, even before that, let me tell you that not only this is 54%, but it will take forever for this one to reach the 54%. Why is that? So what I have plotted here is a log of the fraction field. Since it's a fraction, I have put a negative sign to say that this is the fraction of the molecule. So this is like a 10 to the power minus 9, very low fraction, and 0 is 100%, 10 to the power 1, 10 to the power 0 is 100%. And it turns out that at low concentration, let's say you have 1 nanomolar, at low concentration, even if you had relatively high reaction dominated, it will take many hours for the surface to reach 54%. If it were sort of dominated by diffusion, the molecules, the blue molecules coming from the top and slowly landing on the sensor surface, diffusing through the molecule, diffusing through the fluid, then it takes out, it will take even longer to reach this 54%. So reaching this 54% requires a long incubation time. And if you do not wait till that time, there will be a lot of empty spaces where the red parasitic molecules can sit. And that is something we do not want, right? So this is something we want to avoid. So let me tell you the physics of this 54%. Why so low? Why can't I make it 90%? By the way, if you use a very high density, then you can reach the 54% relatively quickly. So the capture probes that you have, often you will see in the recipe, they say that use a high concentration and you incubate overnight, prepare the sensor overnight before you do the detection. This is why. So let me explain how the process works. Assume that you have a sensor surface like a car parking lot. Each has a slide slots, and the cars are exactly of the same size as the parking lot. And so you can see as the molecules are coming down, they will sit on this surface. Even if it's not successful, if the same molecule comes here, it will try again, diffuse out, and it will try again. But you can see eventually the surface will be fully covered, 100% covered, no problem. It turns out that this is a fully ordered structure, 100% coverage is possible if you can ensure that individual sites are exactly equal to the biomolecules. But the biomolecules are relatively larger compared to individual atoms on the sensor surface. So therefore, a more realistic situation I'll explain in the next slide. But in this particular one, you can simply compute the rate at which the molecules are arriving. Let's assume that it's a sticky surface, so nothing gets out. Once it comes down, it gets stuck. And so this is why you have only forward association. N naught is the number of parking spots. And so N naught minus N is the number of available parking spots at a given time. You solve for this and you can see the fraction that is available at a given time, or fraction covered at a given time, will decay exponentially as a function of time. At t equals infinity, it will be 100% covered, which is good, as you might have expected. And of course, this Kf depends on the diffusion, and we have already discussed the relation between arrival time and the fractal dimension. So you can put it in and you can solve the problem. So if you are willing to wait long enough, then everything will be good. In this particular problem, 100% coverage is possible. If you are not willing to wait long enough, or accidentally if you don't wait long enough, you will see only a fraction of the surface will covered, and you will be in trouble, because in the places where things are not covered, parasitic molecules will come in and produce spurious signal. Now let's think about a slightly more realistic situation. That the molecules are larger than the lattice. Lattice is atomic lattice, so let's say it's 2 atomic lattice wide. The molecule is slightly bigger than the atomic lattice. Then, of course, completely different thing happens. Because you see, it is true that sometime they will be able to, when they come early, they will be able to sit. But you see, once these 4 molecules have landed, no molecule can land in here anymore because it doesn't fit. The car is bigger than the parking spot, and so therefore this will not be able to fit. So this space will be wasted. And similarly, if it comes down here, it will not, although there is a space here, it will be reflected back, diffuse around, and then eventually it can come back. But there will be many places where there will be this gap and it will not be filled. So correspondingly, parasitic molecules can come in and get absorbed here and cause us trouble. So let's do a calculation associated with how molecules land on the surface and what fraction of them remain, what is the ultimate coverage that is possible under these conditions. Remember, I want to explain where is that 54% number came from. So that is what we are trying to get to. And the picture, instead of drawing this picture over and over again, I'll be drawing a slightly simpler picture. You will see that the 2 blue molecules connected by a deep blue connectors, that is essentially represent this pair of molecules. And every once in a while, you will see this empty whites. The empty whites are the places where the molecule cannot sit. These are individual spaces. And so there are a bunch of molecules which have sat in their respective places, leaving behind a bunch of white spaces, and I want to know how many white circles do I have on average on this surface. How do you calculate it? It turns out that there is a very simple recipe. Assume that at a given time, let's say after a minute, you have a situation where you have this long chain and only 3 dimers have landed. Now you have how many empty spaces you have? You have a chain, connected chain of 7 empty spaces. We'll call that 7 tuplet. How many? But this 7 contains 6 tuplets because you have 1, 2, 3, 4, 5, 6. You have 6 here and a 6 connected chain. So this 6 connected chain one side is displaced by 1, another 6 connected chain makes it 7 connected chains. 7. And it will have 3, you can check that if you want to have chains of 5, connected chains of 5, run of 5, then you have 3 of them. In this particular case, you have 1 5 tuplet, 5 empty spaces connected, 2 4 tuplets because you have 4 and 4, and then so on and so forth. And you can then write the equation when the next molecule comes, how the number of tuplets change as a function of time. So this is a 7 tuplet, consists of 2 6 tuplets. When a new molecule lands, you see what will happen. It can either land here on the first 2, right? on one end. So a 6 tuplet is destroyed because now I have only a 5 tuplet here. Or it can land on the other side also. So a 7 tuplet is destroyed, simultaneously destroying a 6 tuplet because I now have just 5. And finally, the molecule can land anywhere in between of the 7. And you can land here, it can land here, it can land here. So the number of empty spaces, it will destroy, all of them will destroy the 6 tuplets. And so we can write a differential equation for it and then solve it as a function of time. You'll see that that will give us why the coverage is never perfect. So let's do the counting. Assume M is 6. So I'm trying to count the probability that a 6 tuplet will be destroyed. This is equal to the probability that a 7 tuplet is destroyed. And the factor of 2 says that I have the 7 tuplet on the two sides, the first and second set. Here 2, here is one probability, and here is one probability. So this is one way the probability this 6 tuplet can be destroyed is that a 7 tuplet is destroyed by a pair. So that explains the second term. And the first term, well, it simply means the number of places this dimer can sit in the 7 tuplet chain, in this chain. And so therefore this is m minus 1, choose 1, because you can just sit in any of the m minus 1 places. All of them destroys 6 tuplets. Easy differential equation. The solution is known. You can just put this solution in here, and that will give you immediately, if you put it in here, it will give you for dp1 dt, the probability that you have a single isolated open space will be given by this simple relationship. And once you solve for it, you will see that eventually at the end of the day, after a long period of time, 1 over e squared of the white spaces will never get erased, because this is at the end of the day, there will be all these duplex sitting there, but these empty spaces will remain, and the number is 1 over e squared. So let me explain how they feel. So they feel, first of all, if it were direct, if there were no space restriction, then it will fill relatively quickly and eventually saturate. But if you have this type of sequential absorption, when they are trying repeatedly to fill this space, the saturation will be very, very slow. And I'm simply calculating this probability, 1 minus this, to see how they saturate. And you can also calculate how doublets, triplets, and all other big spaces, how they disappear as a function of time. This is the rate at which the doublets as singlets disappear. Doublets disappear and the triplets disappear this way. Bottom line is that in all these cases, a fraction of the space will remain unoccupied. So everything I did was in terms of a lattice. So in terms of a continuum, then what will happen is that you see every time you have the empty space, you have two lattice sides which are empty, and the number of white spaces were 1 over e squared. So in terms of total amount of space it took up was 1 over e squared. These ones are also lattice spacing, but these are not really wasted, the solid blue ones. And that will be 1 minus 1 e squared. The rest of them, each one of them has 1 lattice space. It takes up 1 lattice space. So this is the total number of empty spaces. But the real empty was these ones, the ones that are associated with white. So there's 2 divided by 1 over e squared. If you divide it out, you will have 23%. And so in 1D, no matter what you do, you cannot get more than 76%. And in 2D, no more than 54%. This is why, this is the statistics of random sequential absorption fundamentally precludes us from achieving full occupancy. So it turns out that as I mentioned previously, that in 2D, at high concentration, it reaches the 54% relatively quickly. 1 millimolar, if you use 1 millimolar target concentration, or receptor concentration, it reaches it relatively quickly. If you use a 1 micromolar, then the blue line says that it takes quite a bit. And as you lower the concentration of the target molecule in order to lower the price, let's say, of the sensor, you have to incubate more and more. And especially with the diffusion limit getting to 54%, the saturation concentration will take a very long time. Now, are any of these experimentally verified? I mean, you know, this is a very strong statement that you will have 55% unoccupied area where molecules can land in. It turns out that you can indeed do so. So on the left plot, we have the receptor molecules randomly decorating a planar surface, let's say. And you see that this is at a given time. And you can see that all these empty spaces where parasitic molecules can come in and corrupt your signal. You can try to fit a circle in this empty space to see what fraction of the space is really empty. And these circles are these big red circles. It's simply saying that what fraction of the area is empty. And you know, at saturation, this would be 54% would be occupied by the blue, and the remaining will be occupied, will be empty. But we have not gone to full saturation yet. At full saturation, the gap would be no bigger than individual biomolecules. And at full saturation, therefore, things would be considerably better. But we are not there yet, and you can see large empty spaces in various places. And you can compare with experiment, for example, by looking at that if you incubate a surface with different polyethylene glycol, different target molecule, receptor molecules, then you can indeed show that the experiment and simulation are very close. That says that this is indeed a physical phenomena, that leaving behind a lot of empty space when you're decorating the surface with receptor molecule is a fundamental problem associated with biosensors. And it turns out that that's why one often puts a lot of small molecules. Maybe I step back here. So once you have decorated with the receptor molecules, you can then put lots of small molecules. It's like covering the whole surface with grass so that the parasitic molecules cannot sit in between. And that is often done in order to improve selectivity and reduce this parasitic binding. So this is one way of doing this. And so that in that case, the biomolecules essentially come through this forest and the receptors essentially cannot bind and they will be on top of this blue grass sort of. And that way, the molecule, the parasitic binding will be considerably reduced. The other technique people have used is to use it's a sort of a flat foot, a big foot, so that in that case, they sort of touch each other. And so that leaving behind a smaller empty space. And that way also as well, one can reduce this problem with empty space and parasitic molecules binding to it. So let me conclude then about this selectivity issue. And the selectivity issue, as I already mentioned, that it's a key concern for potentiometric and cantilever-based sensors. Why? Because in both cases, these are in one case, it's a camera for the charge. In another case, it's a camera for the mass, right? Cantilever sensor is a camera for the mass. And so in that case, even when a parasitic molecule sits on the surface in the empty space where there was no receptor molecule to begin with, it thinks that there is a real molecule there. And as soon as it thinks there is a real molecule, then you can immediately see that it will produce a spurious signal. Now, one thing that came to a big surprise to me is that covering a 2D surface, or even a cylindrical surface for that matter, is very difficult. it turns out that the coverage, if you come with the molecules one at a time, as will happen as the molecules are diffusing through the fluid and coming to the sensor surface, that you cannot reach more than 54%. That's the fundamental limit, mathematical limit. And so therefore, and even reaching this 54% takes forever because it's coming through diffusion. And the diffusion, of course, it will try to land once. If it cannot land in the right place, it will go out in the fluid again and then try to diffuse and try to find another spot. So therefore, it's like a person blindly trying to find a parking spot and is repeatedly getting hit by other pre-existing cars in the parking lot. And so therefore, it takes a very long time, especially towards the end, as you're reaching the 54% limit, to essentially find a place and to get towards the saturation limit. So this is why it's very important to do long incubation time. Whether you do a nanosensor, nanobiosensors, or some other sensor structure, it's very important that you incubate the surface. Otherwise, if it doesn't have enough receptor molecules, then parasitic molecules will bind and you will say that I have detected a signal. Actually, it's false positive and it should not be counted as a proper nanobiosensor technology. And the most important point of these two lectures I wanted to emphasize were that selectivity is very important. It can be highly sensitive. You can detect femtomolar. You can have a very miniaturized sensor, which can be implanted or embedded in various configurations. But if it cannot differentiate between the target molecule, incorrect binding, let's say, one way, or if we allow empty molecules to sit without passivating it with like a grass-like pig or other molecules, then you have a technology which is not really very good and cannot be used. So I hope this is a main message that you will remember. In the next lecture, I'll say that let's say you cannot solve this problem directly. This is fundamental, let's say, and the 54% coverage or this DNA binding, you cannot really come up with a new DNA structure that will solve the problem. What do you do in that case? Are you doomed? The answer is no. When all else fail, we'll tag it, we'll amplify it, and we'll filter it. And that is the topic of the next lecture. And until next lecture, take care.